Maybe it'll come running back. All right, we're live. We're live. So, our new so our first thing of the second semester is just to kind of finish. We're a little behind, so we're just going to complete this. So this problem set covers basically, it's all still energy. So it's just a continuation of the last one. It's all about joules, springs, so springs, friction, and power. So the springs will be basically, if you think about what a spring is, when you stretch it or you compress it, you're exerting a force over a distance. So if you looked at the, the definition of work back in the day, work is force times distance. You might go, oh, well, if you exert a force on a spring to stretch it over some distance, there's going to be some energy stored in that spring. So that's the first thing we're going to talk about. By the way, this is not exactly a complete definition, because you guys remember when we said, well, actually, if you're like pushing a block, at some angle, say this was theta, it turns out that the work is actually this force times the cosine of the angle times the distance. You guys recall that? So this definition is it's true if the force is constant, like you're not changing the force, and the force is directed along the line of movement. So then this is what happens if the force is constant and but it's directed at some angle to the line of movement. And then you guys aren't going to know what this is, but just for funsies, actually, those of you in calculus, we're going to start this today. It's going to be this
was
scary.
My greatest fear.
Huh?
This was my greatest fear.
This?
The funny squiggle.
Do you know this funny squiggle?
No.
From emails?
That's the problem.
Oh, okay.
It's like
Anyway.
that's where my knowledge ends. The squiggle.
So don't worry about it. But all I'm trying to show you here is that this is your definition in like in kind of a limited case, and this is your general definition because what if the force is changing, right? What if as you are pushing the thing, the amount of force you're exerting is getting bigger or smaller? Things get complicated, and you have to start using calculus. So anyway, this isn't a calculus-based class, so don't worry about it. But I guess what I'm getting at is what we're going to have to do is talk about. We've done this a little bit before, but force, and then here's the distance. So, do you guys remember those problems where the force, like, we did a few that looked like this?
Yeah.
So, say the force started at 0, it increased to some maximum amount, and you maintain that force, and then you decrease the force as the thing, like, as you kept pushing it. This area here would give you the work. Does that ring a bell? I'm trying to build a little bit of review here. Hopefully that's slightly helpful. But and that's exactly what this says, actually. So things to come for you calculus people. There's going to be something involved with this and area. So in any case, we're going to actually start with number 2, and then we'll use the formula we drive in number 2 to look at. So when you take a spring, so say there's the spring attached to a fixed thing. So let's say you you stretch a spring and you displace it. So you take the spring and you stretch it out some distance x. Okay. So here's your hand. I guess. It's not the best drawing, but hopefully that gets the point across, right? The spring used to be this long, now it's this long. Yeah, makes sense? Okay. So this distance, the amount you stretched it is we're going to call that x. So how much force was required at the very beginning? 0. Everyone okay with that? So if I'm going to graph force versus distance, then my initial force, like when I just started pulling it, didn't require much force, right? So you start off with like close to nothing, right? And then how much force does a spring, how much force is required to keep that spring stretched? Does anyone remember this one? If the displacement is x? It's a really complicated formula. F equals kx.
Oh, that's what I was. That's what I didn't know if it was the right track or that.
The spring, remember guys, the spring force is kx, okay? So in this form, remember springs exhibit a linear behavior, right? So if you double the displacement, you double the force. So in this formula, x is, it's called Hooke's law, by the way. You don't have to know that. You've heard of Captain Hook, right? He invented this law. So he used a bunch of springs on his ship, and so he named the law after him. And he's trying to capture like Peter Pan or something. Anyway, so the spring force is k times x. K, or what's k? Spring constant. How many newtons per meter? So newtons per meter multiplied by meters gives you newtons, right? So anyway, once you've actually gotten to that final distance of x, so then what's the force? What's that? What am I going to put here? Hint. Just kx, right? When you stretch a spring a distance, a displacement x, the force required is k times x. How much force was being exerted when it was halfway? When it was like halfway stretched? Half of kx, right? It was halfway there. So I hope this is getting through to you here. So when you stretch a spring, at the very beginning of the stretching process, there's very little force required, pretty much zero. As you stretch it, so as x increases, the force increases, okay? Now we're going to use this idea here because this is force times distance, and that's what work is. This is going to tell me how much work was done to stretch the spring, which will hence tell us how much energy is stored in the spring. So, okay. All right. We got to use some extremely complicated mathematics here. Should we do calculus? No, it's a triangle. Area of the triangle, what's the area? 1/2 times the base times the height. So that's going to give us, that's the formula right here. The work that must be done to stretch the spring is 1/2 kx squared. Or again, k is your spring constant, how many newtons per meter, and x is the displacement. And then you say, well, doesn't the work tell us something about a change in the energy state? Right? If you do work on something, that's energy, right? Work is energy. So what this is telling me is that, like, because what happens if you stretch a spring and then you let go? Ooh, energy, right? Movement. So this is, we're going to call this the you guys remember what U stands for? The potential energy. Yeah. U stands for potential. So this is what we call this is when the spring is stretched, right? You say, oh, it's not moving. It's not certainly not kinetic energy, right? It's potential energy. So it's very similar to when you lift something, right? When you lift something, it's not moving, but because you lifted it, that's potential energy. So if you let go, it's gonna. Here's a big brain question for you. I just said that, Lindsay, can you put that away, please? when you lift something, you store potential energy. Spring is the same kind of thing. How come this is such a different formula? What's the difference between lifting something and giving it potential energy versus stretching a spring and giving it potential energy?
Because of the ratio. It's something to do with ratio, because like when you have a pencil up here, but then you drop it, it's doubling because of gravity, but the spring is the same rate. I don't know.
I think it's touching on something. Yeah. It just has to do with the force. When you lift something, does the amount of force required to lift it change as you're lifting it? No. Like if this was 1 kilogram, then it would require 9.8 newtons of force to travel upward at a constant speed. Whereas when you stretch a spring, that spring force is increasing the whole time. So anyway, so does that clarify it? So anyway, with gravity, we basically were able to just use this. The force is mg and the distance is h, the height, mgh, whereas the force is changing. So okay, well, that was number 2. Deriving. So for number 2, we want to have a force versus displacement graph, and then just a pretty simple derivation of this famous formula here. And then why don't you use that to solve the rest of the questions on the front. We'll touch base in a couple of minutes to see if you got them all right. How's everyone doing? Is this making sense? Like, you have a question? Three.
No. It was probably answered.
What do I take? Don't forget, when you're dealing with centimeters, you gotta be careful. Because all spring constants are in newtons per meter.
Oh, I've been bamboozled. I've been bamboozled.
So it's like
30 centimeters is 23 meters.
Huh?
30 centimeters is 23 meters.
That's correct, yeah. So yeah, like for problem one, for
I knew it was
example,
big.
the x value is the displacement is 30 centimeters. That's 0.3 meters because you got to divide by 100.
I've been
You've been had, Trenton. You've been had.
yes, it's like that.
Pick one over to this.
This is, I got 300 centimeters. You got 3 meters.
Way to come on.
Oh, okay, thank you. Forgot to do that. 300.
I just. I killed Stacy. Biggest thing. Yeah, I got Yeah, same.
Okay, ready to just check some answers? not gonna like do them all out, but who wants to share their answer to number one? Anyone?
36.
36? Joules? Question says, how much energy is stored?
Oh, it's
So
not
that-
the cost.
That would have to be joules, yep. Number 3,
300.
Yeah.
300 newtons per meter. Yeah, make sure you focus on the units too. Because this one's asking what's the spring constant, so 300 newtons per meter. You okay with that? Okay. And then 4, what do we get? 0.4.
Meter.
It would need to be. Okay, so you found like a 0.5 was the X required.
Yes.
So
Oh.
No, the
because
X
you
required
subtracted
was
from the-
47.
Oh, gosh.
okay,
So
so
it
the
needs to
X
be
was
compressed down to 57.
okay. Does that make sense?
Got it.
So
Yes.
so 4, if you do the math, if you're so our formula is the formula you want to look at, of course, is the one we just talked about. And so if you plug in, ooh, what was that?
My phone won't turn off, and then the emergency calls someone. We're okay.
So if you plug in 1,000 newtons per meter for K, and you plug in 80 for the number of joules, and you solve for, X, let's make sure we're on the same page here. What did you get, 0.4, Trenton?
Yeah.
0.4 meters. So then you say, well, the question is actually asking if the natural length is 90, to what length do you have to compress it to? Well, yeah, so if you're a spring and you have a length of 0.9 and you compress it down to a length of 0.5, then you've achieved the 0.4 displacement that you wanted. Does that make sense? So, and maybe if you want something more formula-y, the displacement is the difference between the final and the initial lengths of the spring, right? All right, let's do number 5. Tells an epic story. It's like Lord of the Rings, but even more epic. No, just kidding. But Lindsay, put that computer away, please. So this question is going to get at a really basic question, which is we're going to start putting attaching a mass to a spring, okay? And in a lot of things we've done, the mass ends up not mattering. For example, if I drop something, right? If I want to ask a question of like how long is it going to take for this thing to fall, does the mass of the thing matter? No. But let's say we're attaching it to a spring. Say we're going to launch something with a spring. Does the mass of the thing you're launching matter? Let's see. Well, here's a little mass. I'm not sure where it's going to go exactly. The idea is if I stretch the spring, I store some energy in here, and then if I let go, whoop, dropped it. Okay. If I increase the mass, I stretch it. You ready? Not very exciting. Okay. So what you're going to find in this, like number 5, is going to walk us through this process of looking at the total energy and the movement. Does that make sense? Why, if you have if you're making a Nerf gun, right? Nerf guns a lot of times. Well, some of them rely on compressed air, but some of them, a spring, and then you make the little foam projectile way heavier. Well, it's not going to go as far, right? So, okay, let's get into it here. So number 5 says you got a spring with a spring constant of 500 newtons per meter, and it's attached to a fixed block. So go ahead and calculate the work. If you squish the spring down, let's calculate the work. work is 1/2 times K times, what's X in this question? It's compressed a distance of 60 centimeters, so that's gonna be 0.6. That's getting squared. So what does that work out to?
90.
90 exactly?
Yep.
We're okay with that?
Yes.
Okay, great. So it takes 90 joules. What value is irrelevant in this calculation?
The start.
Heard someone say it, the mass. Okay, so when you stretch a spring, and here's why, like here's a spring, okay? If I just happen to stretch the spring using this tiny little mass, okay? I mean, who's doing the work though? I am. I'm the one stretching the spring, so it doesn't matter if I use the small mass to stretch it or if I grab the heavier mass and stretch it using that. So it doesn't matter. I know this one's talking about compression, it's the same thing. Compression is just the opposite of expansion. So right now the mass does not matter. Okay, how much work was done to compress the spring does not really matter how big this block was, how heavy it was. So now B hopefully is pretty easy. What's the answer to B? How much energy is stored in the spring right now? 90 joules. Okay, so here's the answer to question A. The answer to question B is that this potential energy is 90 joules. So that's just the work energy theorem. That's all that work energy theorem is. Just says if I did 90 joules of work to compress the spring, then the spring contains that much. Did we watch that Zoolander clip in this class? The files are in the computer. No. You guys ever seen that movie? Zoolander?
I've seen it. It's like the worst.
The worst movie ever? It's not. No, it's the worst.
It's pretty bad.
I remember watching. I don't remember the storyline.
I was just reminded because I said the energy is in the spring. There's a scene in the movie where they're like, the files are in the computer. And he's like, he thinks they're like physical things inside the box housing the computer. Anyway, so C is what's the total energy of the system before the spring is released? Total energy of the system. 90 joules. Okay. Almost a little tricky of how easy it is, right?
Yeah.
Total energy is 90 joules. But that's just to get you to think about like, okay, well, right now, the way our understanding of these systems in the context of energy is there's three kinds of energy right now that we're aware of, right? I mean, you're probably aware of other kinds of energy like heat, but for our purposes, there's gravitational potential energy, there's now spring potential energy, and there's also kinetic energy. Okay, so D says, if you release this, what happens to the energy that's stored in that spring?
It's pushed on into the block.
Yeah, so you could phrase this in a lot of different ways. You could say, oh, the spring is going to exert a force on the block, which causes it to accelerate. But since we're talking about energy, we're just going to say that the potential energy of the spring is transferred into the block's kinetic energy. Does that make sense?
Yeah.
So the potential spring energy is converted into the kinetic energy of the block. Okay? So the spring is like, hey, take my energy. I got squished. I got all this energy inside. I'm going to give it to you, Mr. Block. And when the block gets it, so as the block is sliding, he hasn't really started to go up the ramp yet. So all that spring energy was converted into kinetic energy. So how will we figure out, well, let's actually do an accounting first. So for this moment here, question E, what's his total kinetic energy? you're getting ahead here. I just want to know how much energy does he have? 90 joules. If there's any future accountants in here, this is very much like accounting. There's $90. Where is it? You have to account for it. You got to be like, there's 90 joules in this system. It was stored in the spring. Well, now it's stored in the block's movement. Did any of that 90 joules go into gravitational potential energy yet? Nope. Not yet. Soon we'll throw in friction and air resistance, and then that's kind of like when you have like some embezzlement, some theft. You go, oh, there was 90 joules, but now there's only 85 joules. What happened? Five joules got stolen. So who stole it? Friction, heat, sound, air resistance. Okay, so now you guys who were saying 1/2 mv squared, you were thinking ahead. You're going, well, if I wanted to know, say I want to calculate that velocity. Now I can go. I can say 1/2 mv squared is equal to the kinetic energy. That's big K, by the way. Fortunately, we have little k and we have big K, so you got to be careful of it. So what's the mass? 5. We're solving for V, and the kinetic energy has to be 90. Does that work out to an integer? It does. Amazing. Wow. I think it does. Wow. Astonishing. All right, so we feel okay about that? Now the block's going to reach its maximum height. So eventually the block is going to get up here. It's going to hit its max height. We'll just work over here. Question G. At the top of the ramp, what's the block's kinetic energy? 0 joules. How about its potential energy? 90 joules. Feel okay about that? Make sense? How do we calculate the max height?
MGH.
Yep, so we can equate MGH should be equal to the gravitational potential energy. By the way, in case it's not clear, this is just a little G I'm putting next to the U to indicate that it's gravitational potential energy, since we're also dealing with spring. Maybe a little S here. So anyway, mass is 5, G is 9.8, H is what we're solving for. The gravitational potential energy is 90 joules. And so, what does that come out to be? Like 2, 1, 1.84 meters. Okay, lovely. We'll end a little early today. Are there any questions? I guess before we're done, like anything unclear? Pretty easy, right?
That's pretty
Yeah,
straightforward.
pretty straightforward, hopefully.